should hear. What's wrong with the audio? Can you hear me, Jack? No,
Hello, sir. Yes, I can hear you.
This is on. Mic should be on. Everything should be fine. Wait, he just sent some chat. Yes, I can. Okay, that's great. Thanks. You can just say, like you just say it. All right, thanks. High deflating control. All right, so that's good. So everything's set up. Why did it do that so late? Oh, because you just, all right, I'm gonna mute you now. There. All right, I can't hear, oh, by the way, I can't hear you. Your mic is off. So. Anyway, so let me get rid of this. So the homework, huh? Let me just, oh, that's a big problem. Why? Let's see if that thing projects. That guy's working. That's working, not focused, but so all right, that worked good. Yeah, the system's kind of messed up here. This homework 5, so everyone did okay on it. The one group's missing the didn't turn it in late or something, right? But because there was some mix up on, but the guy, the 10A guy, is one of you guys 10A? No, 10A is not here. Anyway, he claims that he emailed. Are you guys the guys in that group or? Okay, he claims that he emailed it to you, the 2 answers, but he also said he did that the week before too. Yeah, no, I asked him to send the emails. Anyway, I'll figure out kind of what's going on with it. I think there might be just a mix up, though, some kind of mix up, but. Huh?
He told us that he could not do the problem.
Oh.
Because it was busy.
Oh.
He said, if we could finish that would be great.
Oh, okay. I'll talk to him and figure out what's going on. Something's going on. Maybe, I don't know, probably something's going on, Anyway, so this thing, the magnetic tweezers. All right, so I found this thing, that will answer like any question. You guys should play around with this. Let's see, chapter 5, this chat GPT. It's like an artificial intelligence thing.
So you made your comment on that.
Yeah, all right. It'll answer like any question, it's pretty cool. I mean, you should do this. It gives a better answer than like whatever any of you guys write, and even the science thing. So let's see if I can get it to run here. Log in is what I want. How do I log in? Get notified. Do you see where you log in? Oh, email. All right.
Like we didn't use the term GPT. I saw you make some.
I mean, I think you should. I was playing around with it. You can ask it exactly the question. See, I put in like the paper. There's a question about the paper and about how to fix a Grossberg blob model. This thing would give the answer to that without any problem, like a really nice answer, well formed, even on some specific thing like that. So anyway, I encourage you to try to use it and see and compare what you get with that, because one thing about it is that it gives a really logical sequence, like it organizes the answer in a certain kind of logical way that makes it really readable. So that's something you could learn from the computer. It can teach you how to do that.
The formula that you say we should formulate for the.
It comes up with a formula. Yeah, and it's a pretty good formula. It isn't like wrong, So say I asked it like write the formula for modifying the Fourier-Huggins equation with the salt concentration. And it comes up with a very logical answer, well organized, and it gives an equation that's kind of good, So I mean, I don't know, you should probably be looking at that. Anyway, some maybe, I kind of doubt it but from looking at the answers, but basically people should be looking at that and saying like, this is how you organize something like logically in the sequence that someone can understand. Like it always begins with like a broad background. So it's like a funnel thing. And then it gets to the point Then it kind of ends with some kind of broadening out. So it's good. I don't know. I mean, I'm not saying you should cheat using it, but some people may be, so you it should be an even playing field, and if this one's free, some of them you can pay, but this, I don't see how you're going to get better than this, because it's like, it can answer anything. It's pretty cool, but let's see. I don't know, maybe I can't sign on here or something. Oh, check my email. Oh, okay. All right. Sorry. I'm not good at reading instructions. Let me get an email. What's in, anyway, you guys can play with it, right? Just try it out, because I can't, I don't want to spend time like messing around with that too much, but anyway, you tried it though, right?
I tried the equation.
I mean, you can just just put in, yeah, anything you want. I mean, so it can teach you how to organize your thoughts and put it down on paper. You know what I'm saying? Like, you can see an example of a pretty good answer. Maybe they don't give it, anyway, there's some limitations to it. But definitely, and you can pick out like when the computer wrote it, I think, kind of, because it's not your voice for one thing. So, I mean, so basically you can kind of tell, maybe sometimes you can't tell. A lot of times you can tell. Anyway, it's a tool, it's going to be around, it's going to be more and more like artificial intelligence. So now's the time to kind of pick up on it.
I think it's going to kick out gold.
I don't know, it can answer any question. Yeah, you can just type in, like I asked it, like my daughter got in a car accident in Los Angeles, like, who's a good lawyer in Los Angeles to handle this thing? And it came back with a whole thing. It told me how to do it, like, you're right, it could replace Google, because it's actually thinking. Google isn't really thinking, so yeah, it came back with like an essay on how to hire a lawyer in Los Angeles, California. It's like, but it can also answer the math questions and things. Like I asked it, how's a Fourier transform like a symphony? And it came back with an essay that was like really good. Like, you get a PhD by the answers that it gives. So it's kind of funny. I mean, it's the kind of answer, like if you got that in a PhD qualifier, you're like, wow, this guy's smart. Like, it definitely would pass it. So I mean, I would mess around with this thing a little bit and see kind of what's going on. Anyway, the link to it's there. And I think I gave it my Google password or something to get into it. So, but yeah, I'd have to go search my mail, and that doesn't work in here. Anyway, it's linked under homework 5. Like, the first thing I've stuffed it in there, ChatGPT, before the coil thing in that coil. Anyway, let's see. So where is yeah, so that's something I read an article or something about it, and then I looked it up and I started doing things with it. It's like, wow, this thing can really do it. But it doesn't write a paper for you, but it'll write it writes like 4 paragraphs on a subject, whatever it is. So it's not writing a whole paper. There are ones you can pay for that write a whole paper. So anyway, so have you guys heard of that before, or that artificial? Yeah, all right, because I kind of heard of it, but I didn't realize it was so powerful. Like, I mean, it can answer these questions. Like, you can put these questions into it.
Improve their mathematical feature,
Mhm.
they've been able to derive some equations.
It can already do it. It already derived it. I already asked it. I asked it for an equation. It gave me the equation, and it was pretty reasonable. But when I put the paper and I put like, I'm not sure you have to do this, but I put like Lu, Go, Gao, Li, on Zhang, and then I said,
Yeah, it's very powerful. Summarizing a paper.
it can do it. It's totally right, when it comes through. It's just like sometimes it's a little bit too broad or something, or it's not exactly to the point.
Yeah.
Actually, rarely. Actually, it gives a perfect answer almost every time.
But I guess in the other way, you also have to have knowledge of whatever you're asking. Yeah, you're asking. Yeah.
It
So that
doesn't.
you'll be able to pick. It's telling you something that is outside.
It's never been wrong though, and it can answer something that's even conceptual, like what's the Fourier transform have to do with a symphony? Like, there's nothing to connect them. You're not going to find that on Google. And it came up with in other words, Fourier transform, you have a noise pattern, it can decompose it into these pieces, and a symphony is made up of all the instruments that can be put together to make the whole. It's in that sense, they're the same, kind of similar, and it picked up on that like immediately. you know, so that's not something you could program. I don't know how you program that. Like, you know, it's not, so there's other things, it's really kind of like a game to play with it, see if you can stump it, you know, but I haven't been able to stump it yet. Anyway, so there's that thing. And then this is just kind of go through the papers. I said like before, that when you're asked about equipment, that you should start with how to build it, you know, just how the pieces are. And some people did that, some people didn't. And then yeah, but all right, put this into the I whatever it is, the iChat thing, whatever it is, and it'll come back with a very coherent answer. It can answer this thing. What is a magnetic tweezer? It can come up with a perfect answer for that, you know, because it's just a straightforward, just what is this thing? I mean, put that in, you'll see like it just perfectly describes every bit of it. So I mean, just see what it gives for it and compare it with what you put down. You'll find out your thing isn't. It has a logical sequence, you know. It like presents you like the broad picture and then like narrows it down. It tells you how the pieces work, how you build it. Everything you want to know is there, and it does it in 3 or 4 paragraphs, you know. And if you look at your thing, it's like it's kind of wandering around. It's like you're looking at a bunch of different things and you're piecing them together, you know, and you can tell. So it's like it's not coherent essay thing, you know. So that's how it can teach you how to do it, you know, how to write something that people can understand versus something that's just, yeah, you understand it, but it isn't really coming across, you know. It's important to be able to do that. That's like the whole game, right? So anyway, I think we can learn from the computers with this thing, you know. It's better if you do it, you know, like you're not going to learn anything if you just type in and get out, but basically it can teach you how to do something coherent, you know, write something coherent. And it can show you also, it doesn't have to be really complicated. It can be simple, but still convey the point, you know, like the salient points. So I think it's pretty good, you know, but so Lou proposed, like Lou proposes this whole kind of new way to look at it that has to do with this pulling out these 31 unit mer unit chunks. So it's different than the Grossberg thing. There's some base, and then he has this folding, so he has multiple steps. In fact, that question's answered in the last question where it says like none of this is in Grossberg. So that quote you could just stuff into the nuances part of B. That answers B, the last part, you know, it's kind of already in here. And then the LCST, everybody got that, I think. Efficient thermally driven. Then how does salt? So write an equation for salt. So again, you can see the answer that chat thing does. It gives a pretty good answer. It writes an equation. It doesn't skirt around. Like a lot of you guys skirt around, like I don't want to stick my neck out and give an equation. But so it just gives you the equation and it doesn't care. So that's kind of what I'm looking for. So you just write down, well, maybe chi is proportional to this, or proportional 1 over the salt. And then you have to go through and then put in test things that you know, like at high salt, then you have no, at high salt, you don't have any interactions anymore, if they're polar interactions. So it has to get rid of all the polar interactions, which includes the thing that drives miscibility and the thing that hurts the entropy. So both A and B get affected. And then, so your function has to have both A and B is concentration dependent for the salt, I think. And then what that dependence is, I mean, you can figure out. So you could just propose that it's proportional or inversely proportional, or it could be a power, or it could be some other function. Or you could put in the device screen like that, do it. If you wanted it more complicated, which is 1 over the square root of the concentration. So you can make it as complicated as you want, but writing some kind of equation is like kind of what you need to do to answer that, right? If you write some kind of equation and it's wrong, then you got like a 95, put it that way. And if you don't write down an equation, you got like an 80.
So basically what you need to do is an equation.
Yeah, you need an equation. I don't know what I asked. How could this be incorporated into this Huggins equation. It means you have to write,
What's
yeah, you have to write a new equation. So you can start with that equation, saying just incorporate. So you start with that equation. How do you have to modify it to put in that there's a salt concentration dependence to some of the terms. So it's not going to be the combinatorial entropy term, the log term. The two log terms is going to be the interaction term because it's screening the interactions. It's probably going to involve the Debye length. I mean, so 1 over the concentration squared, a square root of the concentration, and then so yeah, you should write an equation. I mean, and don't feel timid about doing that. That's how you're going to make have predictive ability. You have to write equations, right? So, and it might be the wrong equation, but basically that's the point. Like you propose and then test. So what do you know about the salt? Well, it's going to go, if the salt goes up, the interaction is going to go down. So it should be, that should work, you know, in both the water organization and the attractive interaction between the polymer, like the hydrogen bonding goes down, but maybe in different ways, you know. They're both hydrogen bonding. So you could figure out how it would work, you know. Anyway, the chat thing will give you an answer. You can look at what they did. And then this could actually simplify talking about these quizzes. Like I just give the chat answers and like, that's it, you know, doesn't result in. So this is just talk about what he talks about, you know, basically kind of reiterate what it says here. He gives some evidence for it, like in his measurements as the steps that are at 31 repeat units. And then nobody mentioned the thing that basically the 31 repeat unit is basically a Kuhn step. Like one of the groups kind of mentioned it, but that I thought would be, because I talked about it in class, I thought that would kind of come out that this loop paper is really kind of bogus. Like his whole 31 unit thing is wrong. That's a Kuhn unit. That's a step unit of the chain that he's pulling out. So there is no little ball. Like he shows this. So his proposal is totally wrong. Like there are no balls.
I know we did mention, but then we
Yeah, you didn't do it strong enough. You have to come out and just say this guy is wrong, you know. There are no 31 units. That's just a figment of his imagination. He makes them into beads because he saw in Grossberg as beads.
We did mention that it's kind of like its own thoughts.
Most of the groups didn't say anything about it. You know?
Literatures enough to support that.
Yeah, the bead thing isn't right. You know, it just isn't right. So I think you should just come out and say it isn't right. Like it's not right. There are no beads. That's a figment of his imagination. And then what they are is the Kuhn steps popping off. Like that's why it comes out in units, because they're Kuhn steps. And this thing has huge Kuhn steps, and he doesn't even know that this polymer has a huge 78 or 80 angstrom Kuhn step in it. You know, it's huge. Usually it's around like 5 or 10. It's just big. I mean, it's almost like a protein because of that. So anyway, all right.
How is it published? Or is that like they figure out?
No, I mean, all right, things that are published aren't right, you know, they aren't necessarily right. They got through a review. So you send it to a paper and you suggest who you want to have review it, you know. And sometimes the editor will just take who you said to review it, which could be corruption, I guess. Yeah. Yeah, but it's the same. The reviews are going to be the same. It doesn't matter what journal. Like the referees, everything's going to be the same. The editors might be harder, but the reviewers are going to be the same people, no matter where you publish it. And I mean, basically, more than half the stuff out there has probably got some kind of problems with it, you know. There's nothing wrong with that. Like he proposed something. It isn't like he didn't believe it when he said it, you know. So he believed that this is true, and like he's getting these blips, like these 31 unit blips in his curve.
New discovery on his own side.
He's pushing it far because he thinks it's like, oh, this is a new model, like a new discovery, like so new compared to what's been around. This idea that it collapses down. He's got this new idea that has these 3 stages, you know, and he's pushed that along. So he has so far. But he never, at the first step, he never said like, what is the Kuhn step of this chain, right? If he had said that at the beginning, you would have realized there is nothing new here. This is just the same as Grossberg, except where the polymers get huge Kuhn steps.
Okay.
right? You didn't do the first thing you have to do when you're doing some kind of thing about single chains, like what is it you're working with? Is it this flexible chain that's got 1 angstrom steps, or is it this thing that's got these gigantic linear pieces, that could come off as a unit. They're kind of hooked together. So I mean, and also it's got the side group is like a sheet because it's got that resonance structure between the carbonyl and the amine. So that means it's even got rigidity in the side groups, and that kind of enhances the persistence of the thing. So it's got all these, it's like cards sticking off a string, and the cards are pushing each other apart. They can't overlap, so it's steric interaction. So anyway, it's a pretty good example of how you can mislead yourself. And I don't blame them, but basically you have to kind of say, well, this isn't true, that isn't how this thing works. Apparently, if you do the chat thing, it comes out with all stuff that he's published other stuffs on protein, on protein unfolding and folding, where he pushes this idea of like substructural pieces coming out, which could be true in proteins. Like you have alpha helix and beta sheets and things, and there's other kinds of helices and things. So, but then he's trying to apply it to the synthetic polymer, and that's kind of where I don't know. There's not really any excuse that he didn't know that the persistence is so large, that in this thing. Anyway, so no one really pushed that point. It would have been nice to see pushing that point. Then the artificial muscle, I put a paper up there. Maybe I put it up too late, but there's a paper review paper on artificial muscles using hydrogels, which PinnyPam you make a hydrogel with it. You cross-link it, and then it becomes this hydrogel. It changes shape. So it's pretty good. It's in this Advanced Science News something. It's a pretty good journal, I think. And it kind of goes through how you use PinnyPam to make muscles. Like so you have one layer with the expansion contraction. You can make the thing curve, and it looks like it's an arm type thing, or whatever. So maybe it's not gonna be an implant or anything, but it could be like a robot picking up plastic bottles or something, who knows. So it's an actuator, in the end. But anyway, so I thought people would see that. Maybe you guys didn't see that or something. Anyway, there's a paper there about artificial muscles that might be worthwhile. All right, so that's about it for this thing. Any other questions or anything on this thing? Hopefully that's okay. Anyway, it was good. Like everyone did well on it. Everyone got above a 90, except the 2 guys that haven't turned it in yet. But so I think they'll probably do well because they heard this thing. So you should be able to just give whatever I just said if you want, or you could just use that chat thing and it gives perfect answer. So anyway, yeah, so we got to I got to go back and I mean, it's probably worth, like, especially with a question like came up with questions on the first one, and just type it into that chat and see what it comes out with, and it might clarify like what's going on. I just describe the magnetic tweezer, it'll just spit out the answer. It's like a perfect answer, almost perfect, except it's focusing on biology. So you'd have to nuance it a little bit. And then you could, if you type in the Lou and say, how is Lou's magnetic tweezers different or something, it might come back with something. But it's kind of worth playing. It's kind of fun to play around with it, and I think that it can teach you stuff. Let me see. I got to get I changed this slide 3. So, I had to go through blobs today because the homework for tomorrow is on blobs. So where is number 3? Looking for slides 3. This one. No, on Friday. Friday, there's a new homework that I'm going to talk about on Friday. So I wanted to go through the background of it today, which is partly the scattering that I did last time. And then it's, let's see. So I have to do this to get enable editing. Updates available. I don't want updates. All right. So, so this is the deal. Like we have, let me just zip down here. we have this picture of the coil like in temperature, right? So you have the theta coil here. It's right on this cliff, and then there's a collapsed coil was Grossberg, right? And then, which he says is a first order transition. So that one should be like a switch, like on and off, like melting a crystal. It's either a crystal or it's a melt, right? So, but it's actually got a little twist to it too. And then we have expanded coil out here of good solvent. So you stick polystyrene and gasoline, you get a good solvent coil, or you have napalm, right? So basically the theta solvent and then the expansion of the thing, right? So, and we said like, well, the original Florey-Kriegbaum just had the excluded volume, so it was just a switch, like the collapse, like on off, like a first order transition. But in order to get it to be like this gradual transition, we introduce this enthalpy term, this chi term. Because that's 1/T, so it gives a temperature dependence to the energy, and then the derivative of the energy is the force, and that kind of gives a radius of the thing somehow out of that. So basically, the temperature dependence of the radius. We get the radius from finally through the Florey-Kriegbaum. You solve for the radius out of this equation, and then you get the 5/3 power law thing, and that includes how the radius depends on temperature in it, because it's got the excluded volume part is 1 minus 2 chi, or 2/T, 1/T term. Anyway, so that explains like why it's got, and you can make that black line, it'll fit the data perfectly using that equation, right? So that's nice, but it doesn't tell you like what's going on. Like in other words, how is it that you could have an expanded coil that's smaller than an expanded coil and larger? Like, how does that work? In other words, there's no cartoon of what's going on here. It's just like this thing, right? So there's a way to do that. So the idea is that, let's see. So the idea is that you have this large thing, right? And then it's got this size scale, this R size scale. And then you have kind of the small size scale, this Kuhn length. And then you're going to do something to it. Like you can change the temperature, you can change the concentration, you can stick it and put an AFM on it and pull it with a force, right? So those are the three things, and there's other things you could do to it, but basically those are the three things we're going to look at. So what happens when you take a force, right? So at long distances, right, and you put a force and you get a larger torque at long distances than at small distances, right? So if you put a force on it at small distances, the effect is going to be nothing, right? But at long distances, the effect will be large. So basically, if this thing was R squared is NL squared to begin with before you put a force on it, so this could be an AFM tip, and you have the polymer and it's stuck to the surface, you're pulling it like that. Or it could be that you have a surface and you grafted a bunch of polymers on it. So in that case, there's an effective force because you have this squishing from the sides, right? You have isotropic planar stress going in that leads to an effective force that pushes it out, right? Or you can have this case, like you have a dendrimer, right? So you have something like this, or you just have a super branch star polymer. So you have this kind of crowding on the inside, and then you have layers that go out. And by the end of this thing, it's NL squared. And by the inside of this part, it's the size goes with NL, like it's a rod. Right? So you have some kind of step L, and there's N of those in it. So the step and the size just goes with N directly versus the size goes with the square root of N for this Gaussian, right? So, and further, like if it's concentrated, you screen the interactions, you have NL squared, and if you go out further, you have R goes with N to the 3/5 power. So the coil even gets more expanded as it goes out, if you have some kind of a star thing like that. That's a theory. In reality, that doesn't happen. But that's a model that's pretty prevalent about, it's called the Dowd, DAOUD, Cotton model. Those kind of star thing. Dowd is both of these guys are pretty famous guys. I think they're both in France. And they propose this model for this kind of star thing. Anyway, this idea that when you stretch it, so when you stretch a coil like that, so it's gonna have a lever arm at a point where it'll break it down completely. and then within it, it's going to be unperturbed. So you're going to have NL squared, if it's a Gaussian, so R squared NL squared at the small scale, and this would be the tensile, kind of a tensile length. And then at larger scales, then that's a tensile. Let's see, this is actually the Kuhn-Step NL squared, and this is the tensile length. The length, like one of these was a coil, you get L squared and L squared. And total chain size is going to be like the number of those tensile things times this tensile length. Right, so you have two equations. So in other words, because it's such a large molecule, it can start making decisions of a cutoff point where the thing you're doing to it is going to impact it, and at smaller sizes it won't impact it. Right. So the small thing is called blob by the French, basically the gens. The gens kind of call it a blob, I think. So anyway, that's how the French dealt with stuff. They had these funny names they called things. So anyway, so that's true of both temperature and concentration. There's a tensile blob. So the tensile blob was actually due to a guy named Pincus, who's at UC Santa Barbara. And then he's an old guy now, but basically he worked with the gens in Paris for a while. And he also worked at Exxon Research Labs in Annandale, New Jersey, right? Like right across the border from Pennsylvania. So anyway, yeah, so he worked at a bunch of places. One of the things he came up with was tensile blob thing, which is kind of an interesting idea. But basically, it's been pretty much verified that things work that way, right? So that this tensile blob happens. So what you do when you get this kind of blob idea is that you do like scaling approach to it, right? So you say, first you can say like if you're for a Gaussian chain, that's the energy. You take the derivative, you can get the force. Then you have these kind of two size scales, R squared and R squared. So when you first put the force on, so say it's a Gaussian chain, you just put enough force, nothing happens yet. Then this R and this NL squared are the same size, and it's the tensile blob is the coil size of the same thing. Oh, sorry. Yeah. All right, so when you first have the coil that's Gaussian and you just put a force on it, nothing happens. So the tensile blob and the coil size are the same. So that means that this R and NL squared are the same thing. Like it's tensile blob. So this one cancels with that. Tensile blob squared on the denominator. So basically, tensile blob equals 3 kT over F. It just kind of falls out of that force energy equation. Right, so you can define that. Kind of makes sense. Like the more you pull on it, so you're going to perturb deeper and deeper into the structure, and what's pushing the structure out is KT. Like each of the mirror units is moving with KT, so it wants to expand into a random structure, but it can't because you're putting a force on it. So those two things are balanced, and because force is going to have force times distance give energy, so you have to have a size that comes out of that. Like just even if you just said there's this thermal energy is driving it, and there's a force, then there's a size that comes out of that, just saying that, right? Because force distance is energy. So anyway, that works. Like you can measure this, you can see that it works, and it's used for things like these surface anchored chains, which is sometimes common on a flat surface, but usually more common if you have like nanoparticles and you want to disperse them in a polymer. So you glue polymers onto it that are compatible with the system, and then somehow that supposedly make things better, right? So anyway, so then you can predict, you can do this. So this is what you do with all these blob things. You do a scaling argument, so you don't worry about the actual size of anything. There's no prefactors. It's just saying like, well, how's my overall coil size gonna be impacted by force and by temperature? Like what's the in fact, you're just looking for powers here. Like what's the power of force? What's the power of temperature to give me the coil size? Right, because that can be easily tested. Like I can stick a polymer into an AFM, put a known force on it, glue it to the two ends, hopefully get one chain. then just change the temperature and either see the size change or see the force change. Like if the size is fixed by the two ends, and the force would change. Right, so it's like an instron test where you're using a hair dryer to heat the thing, and you're seeing that the force changes when you heat it. Right, so anyway, so that's the kind of predictive thing you want to get. You don't care about like what's the prefactor so much. So you don't care about the details, you care about how the thing depends. Right, so that's a scaling argument. A real argument, all the numbers would add up. Scaling argument, the numbers don't add up, but you know the behavior of it. So you get kind of an idea, like if you draw a cartoon of what's going on. Right, so that's kind of the general idea. So to do that, this is the common trick you do. So you say molecular weight of the chain is n, and if you divide by how many of these tensile blobs are in the chain, then I get the number in a blob. The blobs are Gaussian, so NL squared Kuhn length gives me the tensile blob squared, because a little Gaussian blob. So this is R is NL squared for this blob thing, right? But notice it's got the terms. Well, all right, we know that the tensile blob depends on KT and F, so that thing's going to give us an answer in F and T. And then the number of tensile, we have a problem, like that's some oddball thing. So we just say, what is that? Well, the number of tensile blobs is going to be, let's see. So the tensile blob NL squared is going to be, let's see, how does this work? Oh, this is just rearranging this thing to define what tensile blob is in terms of the tensile length. And the tensile length we already know is KT by F. So we can replace tensile blob. Then the overall size is R times N then. So you can replace that with that. And then you have this thing as that. So then you just get this equation that defines the thing that you kind of could have said to begin with, that the more force you put on, it gets longer. And the more temperature you have, it gets smaller, right? And then basically it's power 1 for all those. And if I have no force, or if the force matches KT, so it's just balanced, I have NL squared. So when you have a scaling theory, you want to test that with things you know, like, well, how does it work out? So you have a tensile blob concept, and then when they're actually just matched, then force equals KT, and then you have NL squared for the length, which is what you wanted to have to begin with. And as you stretch it out, you get this other size thing, right? So this thing, maybe you could measure the size just by the extension of the AFM, but you don't know the details, but then you can get this tensile size out of this. So you can say everything about it from that scaling argument, right? Again, there's no details, so it isn't something that's so concrete, but this is the scaling argument thing is a theme for everything that degens. And this guy, Sam Edwards, who's a Sir, he's like knighted in England, you know, that they kind of came up with for, Pincus isn't knighted, so we don't knight people. It's a US guy. So, but anyway, so the other two things to look at, so that's the simplest one, right? So, all right, then there's this business. Okay, so external force. So at large scales, it goes to rod. At small scales, it's Gaussian. But it's backwards from a Kuhn length, where you have Gaussian at large scale, and then it's rod at small scale. So you can see, like, if you have internal things, right, then you get the scaling change at small sizes. Then you have the random at large sizes. If you have external things, you have the perturbation at large sizes. And then see, so there's a symmetry to this. You can apply a force in two ways. It's like you want to make nanoparticles, you take a brick and hit it with a hammer a lot of times. Then you could eventually get nanoparticles. Or a chemist would say, I have a molecule, I'll grow nanoparticles. So it's like bottom up or top down. So everything is kind of like that. So if you do it, this is also like bottom up, top down. So basically you have like the brute force way to get a rod is to stretch it. And the subtle way to get it is to make penny pan that's got 80 angstrom step lengths in it. You know, and the effect of those two things on a material that covers like 3 or 4 orders in size is that you create a new size scale to the thing, right? So something you can't get in metals because they aren't 3 or 4 orders in size. You can only get this in molecules that have this huge separation between the primary size and the overall size of the thing. But in any system that's like that, like humans are basically kind of like that, you're going to see these size scales show up. Right. So in nature, you're going to expect to see whatever perturbation you're putting, either external or internal, then there'll be a point where that perturbation ends, and that's going to generate a size scale. like in general, right, in nature. So basically you're just seeing kind of a law of nature somehow coming out of this, right? So anyway, so that's one part of this. Then the other two parts are kind of similar, but kind of more complicated, right? So we have the other two are when we put in, so you go to concentration, right? So you know that the if it's a melt, the chains are Gaussian. That's the Flory proposition, which was proven, right? And when it's dilute, it's an expanded coil. And when you reach this C star, the coils overlap with each other, right? So there's some size scale where they're going to be Gaussian, and at small size scales, they're unperturbed. So they're going to be expanded coil. So this is kind of an external perturbation. Hope it's not COVID, but anyway. So so we can look at it like looking at the stuff with scattering is kind of the easiest way to look at it because you can't really draw a cartoon of a blob because they're statistical objects, so they aren't really like something that you can say there it is. You know, like you think about like if you have a cable or a string or something lie around and then you pull the ends of it. Well, yeah, it's going to be like generally that's going to happen, right? And the internal part will stay. But like, where's the blob here? There's no cartoon of it. To see that, you have to draw circles, right? So it's not kind of obvious. And the same with these others. It's not something you can actually see with your eyes very easily, or maybe you can't see it at all, right? So maybe this guy thinks he could see it with a magnetic force thing, but he was wrong. You know, so basically, you can't see it. You know, but in scattering you can see it. So you're looking for power law. So we said like in scattering, so there's a limit where the things are going to just like dots, right? And then you're going to see like Gaussian chain. Then you expect to see -2 is minus df, the fractal dimension, so 2-dimensional. And then at some point it's going to go to -1, and that's the Kuhn length. That's also minus df, 1-dimensional. Right, so sorry, that's the kind of picture you have. So say you put in a concentration blob. So you're going to add concentration to this. So first off, it's in a good solvent. So this is 3/5. This is 5/3, or it's 1.72 minus 1.72. That's the expanded coil. Then you're going to add, and it's going to become Gaussian at larger size scales because you can still zoom in and see expanded coil at small size scales. So you zoom out and then eventually you see Gaussian, it's like a melt at large size scales. Right. So that means this thing, all right, so this number is going to be the same because that number is the number of say electrons per unit times the number of units. That number is fixed. And this thing LK is fixed too. So those 2 points are fixed in this picture of things. And this curve has to go steeper. So the only way for that to go steeper is to have it go like here, like -2, and then the blob size is there. That's the concentration blob. Right. So as you add more and more constant, so this tailover part is Guinier's law. That's exponential -q² rg²/3. It's a Gaussian, and that moves to the right, as you add it to higher and higher concentration. Meaning this is Q's 2 pi over the d space, and so if you move to the right, that means the size gets smaller. So your coil's like going down to theta state. It's getting smaller, just like in that curve when you say Rg versus temperature, and it goes down, right? So there's a theta position here, and this is good solvent over here, right? So basically this thing expected to move to the right, and that's what happens. It's gonna just continue to move to the right until it finally is all Gaussian. And that's like concentrated. That's when you reach like concentrated solution. So there's no more good solvent part. So that's how in concentration it eats up the -5/3 as it moves over. This number stays the same. That number stays the same. It's not affected by it. And you just see this transition size get smaller and smaller as you go to higher and higher concentration. And you can draw pictures of this for the tensile one too. I mean, for the tensile one, you're saying that it's Gaussian, you have -2, and then it's going to go to -1. And then as you pull it, then it's going to go to a weaker slope. So it's going to be -1 over here. And the tensile blob size is here. Right, so the RG gets bigger as you pull it with the force. And then this tensile blob size gets smaller. It gets going out, and finally the whole thing will just be an extended rod that ends at the same n squared n, like it's got the same amount of material, the same concentration of rods, and the same number of electrons per coulomb unit. So this number has to stay the same, and this number has to stay the same, and that has to stay the same. So it changes it within that, and that means it has to get longer as you pull it more. Right? I mean, kind of the sketch of that makes you think that's how it works. So anyway, that's this concentration blob idea. And then you can go through, I'm not sure I have time to go through this in detail here. Hide this. So basically, you know, C star, so you plug in R is into the 5/3, right? For the good salt. Oh, sorry. Okay.
What pitch is that?
What is 3? Number 3, yeah. So C star, the overlap concentration is the coil size cubed, and then the mass by the coil size cubed, and there's some prefactor. So again, this is scaling, so you forget about the K prefactor thing. So you just say, and the coil size goes with n to the 3/5 because it's a good solvent. So R to the 5/3 is n. So you can plug those in, you get n to the -4/5 for C star. Then you say above C star, there is no concentration to change anymore. There's a concentration that's C by C star. Everything's normalized by that. And C star depends on n, right? So you say that this blob size is going to be whatever concentration divided by C star, which depends on n, just some power, you don't know what it is. This is a typical scaling argument. You just throw it in, it's a power dependence, because everything in polymers is powers. Everything's like log, whatever, so it's going to be a power. So then you have R is 3/5, the 3/5. So if the coil size, if you're at the point where it's not overlapped yet, so it just barely touches, then R is, these two numbers are the same number. So this thing has to be proportional to that size. This is a typical scaling argument. It's full of like kind of BS things that you say, right? I mean, in other words, that isn't necessarily true, but basically you say that in order to get the right answer. This answer has been proven, right? You can see this in osmotic pressure and in scattering. Anyway, so you say this thing at when they first touch is going to be R. It's the same argument we used in the tensile. So all of them are going to be based on the same kind of argument. And it's got to be some power of C by C star, because C doesn't matter anymore once they overlap. You can't see an individual coil. So you have to normalize it by that touching point. So how far above the touching point are you? That becomes a thing. And this thing depends on n. So you're going to have like 4, and it's 4/5. So it's 4/5, and it's 1 over it. So the minus becomes plus. So you have plus 4p 5, and then the 3/5 from that one. Then this thing has to be that. And this thing, since you're above the overlap concentration, there's no dependence on n. You can't, because you can't see an individual coil above the overlap concentration, so it can't depend on n. It can only depend on concentration. That means that this thing can't depend on n. You have a function of n. That means this argument has to be 0. And then you can solve for p, and then you can figure out what the concentration dependence of the blob size is, and you can figure out what the R dependence, which is 1, it ends up being 1/8. It's typical scaling. I mean, it's a little involved, it's a little bit mind twisting, but basically, and there's a couple lies involved, but basically it gives you an answer that follows like the what you measure, right? So if it didn't follow what measure, they would have never said it, and they would have figured out another argument, I guess. But basically this can be proven that the coil size goes with a concentration of the -1/8 power. You can measure that with neutron scattering, right? And then so anyway, that's the concentration blob. The other one, and again, this is the Dowd Cotton, that's the paper that came from that idea. And again, this thing is also BS, okay? Like this doesn't exist this way. But this is commonly people will talk about this Dowd Cotton model, and you can find papers that go on and on about it. There is no evidence that this happens. Like you have this kind of, the coils are all intertwined at an interface like that, so there's no way that you have segregation of it and a concentration gradient like that. It just doesn't happen. So anyway, I mean, but this is a very prevalent model, you know, that people use to talk about how these kind of star things are. The thermal one, actually, it's kind of simpler and kind of more complex. So that's like top down, and the thermal one is bottom up. So you start with the Gaussian, and then you're gonna like expand the coil from the bottom, so that the local structure, because as the molecular weight, the excluded volume. Let's see, how does this work? Anyway, you start from the bottom up with this one, however it works. But basically, the thermal is on a smaller scale. So anyway, so we have the Flory-Krigbaum equation, which is this thing here, and then you can also make a scaling argument, which is kind of blobbed out here, but basically that the coil size, so this overall size that you observe, well, once you get above the theta point, it's got to be 3/5, and it's going to be composed of these Gaussian blobs. So once you get to the right of the theta, it's got to be good solvent scaling. So you're going to say it's good solvent scaling of blobs. So you have R and then the blob, then the 3/5 power for good solvent. So it'd be R to the 5/3 is N, R is N to the 3/5. And then time the size is this blob size. Right. And again, we already have an expression for R from the Flory-Krigbaum right here. Right. So then you just work through the same kind of N by number of blobs, and then figure out the same thing we did with the concentration one. You end up with this equation. You end up with this equation, right? So this equation looks just like Flory-Krigbaum has N to the 3/5 is N to the 3/5. There's a blob size to the 1/5 to the 1/5, and then the Kuhn length size, the 6/5, which is 2/5, and then the volume is L cubed. The monomer volume is L cubed to the 1/5 gives us 6/5. That thing cancels out. This guy cancels out. Then you have R is this thing and that thing. So those two things are related like that, which makes sense because this is your 1/T thing. This is your enthalpic thing that's driving this whole operation. And basically 1 over the kind of excluded volume gives us size. So as you get if chi is 0, then the tensile blob size is a Kuhn length, and you have a Gaussian, you have a good solvent chain. And as chi gets more and more chi gets more and more positive, so you approach this kind of shrinking of the coil. Let's see, the coil gets larger as chi gets more positive, right? Whoops, wait. Chi gets more positive. Anyway, it works out. You get the temperature dependence of this thing from that. So basically that's the thermal blob thing. So what do you expect to see? So what you expect to see for this is that it's the opposite of this thing. So we had concentration blob. So log I, log Q, concentration blob, we see like -2 at large sizes, then -5/3, and it's going to go to -1, and that's a concentration blob. Right, this is R, and then this one we're going to see the opposite of that. So it's going to be -5/3, and then 2, and then 1. So that's the Kuhn size. That's the coil size. So as you change the temperature, as you drop the temperature, it becomes more and more. So as you drop temperature, this thing moves that way, and it becomes more and more Gaussian. Right. So that good solvent part. So the Gaussian would go up, and that thing would just shrink like that. That's with temperature dropping, and with temperature rising, then the 5/3 eats up more and more of the 2, and it moves that way. So that means that the R increases because it goes, this is log Q. Q's 1/2 pi over the D spacing. So that's getting larger that way. Right. So the two things kind of are backwards of each other. That's the point. You have 2 and 5/3, 5/3 and 2. So the one is like an external, you're applying this concentration and the things overlap at a large scale. And this is like internal, thermally driven, like collapse of the thing. So it's the same idea as what you have with the coil collapse. Like it's like you take a piece of plastic, heat it up, it makes beads that shrink down. So you get a bunch of beads, the thing pulls in. Right, so you're going to end up with this, like with Grossberg, like you have the distance shrinks because you're kind of heating it and it's coming down. then, it melts the plastic and pulls it in. Here you see in that it's the same thing as Grossberg, where this is 3D and this is 2D out here. Except in this case, it's 5/3 D and then it's 2D in here. So it's going to try to become Gaussian by removing these expanded coil things. Right, as if it's like shrinking from inside out. Right. So the one's shrinking from outside in and this is shrinking from inside out. So you end up with the symmetry, right, between the two. Like, in other words, there's always some kind of symmetry to these things. So you have 1, 1, 2, 2, 5/3, 5/3, 2, 2. There's some kind of always a mirror image of the other one. Between this is concentration and temperature, that's external force and internal rigidity. Right. So that's kind of the blob thing in a nutshell. I can go through a little bit more of this stuff like after, but I mean, there's a lot more to it. Like basically one of the ways they proved this is through the osmotic pressure measurements with good solvent coils that didn't match with the Lori stuff with Gaussian. So anyway, so the kind of the homework this week's kind of on this stuff. So I wanted to cover this as fast as I could today. So sorry, I kind of crammed it in, but we can go through it in more detail, I guess. In the past, I've spent a lot of time, but basically finding papers on blobs, there aren't, like, it's not really talked about anymore in a sense. So it's kind of one of these things that's fading into history, but only when people are desperate and they need it, then it shows up, The coil collapse thing's still kind of active. This stuff is less active. This was more active in the 90s, say. So there's other things people are doing now. So it's probably better not to dwell on blobs too much, even though it is pretty fundamental. But so I tend to dwell on blobs, but I don't think that most people aren't really thinking about it. So any questions, anything? Sorry to cram through that stuff, but we needed to cover it to cover the paper for tomorrow, for Friday. So anyway.
So Friday.
No, Friday. I'm just going to go through it. It's Tuesday.
Okay.
Yeah, it's doing Tuesday. Yeah, every Friday I try to go through the paper, right? So hopefully it's enough background for this thing. All right.